I hope my screen is also visible. Okay, let us start the lecture. I hope the midsem answers are already you got the marks, and I received two emails regarding one email regarding a quiz mark, class test mark, and another email related to the assignment. So I'll check those email today evening. Even if you send some email to me for any corrections, and if you think that I have not corrected it, just remind me after few days. I'll definitely check those mail. It's not like if I am not replying, it's not like that I am ignoring. It may be the case that I've read your mail and then I forgot. It may be possible because there are many students. I'm taking two different courses. So if you feel that you have sent a email to me and I have not replied and there was no action taken on it, then just send me a reminder. I'll do that. Okay, I have also received one email regarding a problem faced while installing the ChamSim simulator. So I'll forward that email to my corresponding TA, and then TA will contact you and try to solve the problem. So I hope you are also following that video where I mentioned everything that how to install the simulation, because I have given you a deadline of this week to install it and given you some small task for this week for the project. And by end of this week, by Saturday, I'll upload another video where I'll give you the exact task that what I'm expecting from you, but you won't understand that task if you not installed this ChamSim simulator before that. So try to install the simulator. Maybe if you can post the problem that you are facing in your own group, and maybe if one of you have already solved it, then you can help to other people also here installing it. There is nothing, this help is accepted, and I'll appreciate this help also, that if any of you have installed it successfully, just tell the other people. Understanding the code of the simulator, explaining how to install, those are not considered on copy case. So only thing that I'll on Saturday, the actual problem that I'll share, I'll expect that problem you will implement by your own, so that should be independent. But before that, installing and understanding the code, you can always share whatever you are understanding. That's not an issue. Okay, so let us start today's lecture. If you remember, I stopped in this particular point in last lecture, and I have to stop because of time. So I'll continue from this point. So far in this section, we have explained the concept of cache memory, concept of memory stall, the concept of multi-level cache. All these things explained, and then here this section is saying that the performance of the program performance, that how a program actually behave in a computer. So there are two ways to see. We have a course in CSE called algorithms, and we know maybe you have not this course is, I don't know if you have already enrolled for this course or not. But yes, we have a course there, algorithm, where we our main aim is to optimize a problem, right? And optimizing the problem means we always think about the time complexity. What will be the maximum number of comparisons, what will be the minimum number of comparisons possible, right? So in this way, based on the time complexity, we try to minimize the problem statement. So there are two sorting algorithms. Like this one is called Reddick sort, and another is called quick sort. I'm not very sure that if you are aware of this or not, because if I think quick shot you already know, and if you have already completed the data structure or algorithm course, then I think both the sorting technique you already know what is quick sort. But here it is not much important to understand these two technique. That's why I'm not explaining. Only thing you have to understand, we know that for larger size cache, then Reddick short is a better choice. And you can see from the first graph here that if the size of the k, means the array size, the array that you want to sort, if the array size is increasing, you can see, then for a larger array size, you can see the Reddick sort is giving better performance, because it is taking less number of instructions to execute. It means less number of comparisons are requiring here, you can see, right? And quick sort is getting more number of comparisons here if the number of elements are more. In this sense, the algorithm people will always say that right, because the number of comparison is less. But let us see how actually it executes when we try to run a program in real machine. So this is the clock cycle time required for the same Reddick sort and quick sort here in a machine. So you can see there is a strange behavior here. Just I'll zoom it up. So you can just concentrate on first diagram here. You can, and then the second graph here. You can see again for higher, when the element size is more in the array, you can see the cycle required for Reddick sort is more. This is surprising, right? You can just compare this point here and this point here. See, the cycle required for Reddick sort is more. So this is a problem that normally a algorithm developer will ignore. They will not understand what is happening, right? Because you can see in the first graph the number of instruction is reducing, but even after number of instruction is reducing, you can see in the second graph Reddick sort is not giving better performance. Reddick sort is taking more time to execute. So what is the problem? The problem is the miss rate. The way we have implemented both Reddick sort and quick sort, the number of misses is more in case of Reddick sort, and you will understand it if you go to the next slide. Here you can see cache miss per item, or you can say, say cache rate also means miss rate also, miss per memory access. You can consider the same here. See here, if you for larger size cache, you can just see there is a huge difference between the number of misses observed by Reddick sort and number of misses observed by quick sort. So if this is for 512, here this is the number of misses observed for quick sort, and this is the miss rate for Reddick sort. So since the number of misses are high in Reddick sort, obviously if there is a miss in cache, then you have to go to main memory and fetch the block. So it is taking more time. So why this example is important? You can read whatever they have written in the figure caption. You can read it once. So what is the importance of these three graphs? The importance of these three graphs is, it's not enough just that you it is not just enough that you will understand the basic concept of algorithm and you'll propose some algorithm with optimal complexity and all. You have to understand that how the underlying computer is behaving, or how the underlying memory is behaving. Otherwise this type of situation may arise that technically, theoretically, you find that number of instruction for Reddick sort is less, but when you will actually run it on the computer, based on the computation, it happens like that the number of misses observed for Reddick sort is more. So ultimately Reddick sort is taking more time. So it means that modern days, for a better performance of a software, it's not enough just to understand the software side, or means it is also important to understand what is the underlying structure of a computer. And that's why I think at the beginning of this course I said that why computer architecture is important. Modern days people works on recent algorithms, recent courses like machine learning, artificial intelligence, where they use huge data and then we have to use different efficient algorithms or efficient techniques, right? But ultimately these techniques and these huge data will run on top of a computer. So it means that it is simultaneously also important to propose to propose an efficient architecture such that this type of algorithms or this type of applications should run efficiently. So that's why the area of computer architecture is very important. It was important in past also, and it will be important in future also. And there will be continuous upgrades in this. It will be required in this area to support all the future algorithms of different domains, and AI ML are one such domain. Okay, so that's this is just an example. And software optimization blogging, I think this part I'll explain now. So before explaining this part, I'll advise you to read it once. This whatever explained in this section, you read it once. After all the explanation that I have given, I think you will understand from this section. But again, in last class also I have asked, I've cleared it that maybe some of you, maybe you can think that how this type of graph is possible to design. Can you design it by yourself? Yes, it is possible to design this type of graph by yourself if you use ChemSim. Because if you use ChemSim, then you can set the cache size. Suppose initial you can run this type of algorithm in your computer, means if you can both radic sort and quick sort, you can run in the computer and you can find out the number of misses, miss rate, instructions. So this type of graph you can also design if you know the champ sim. That's why understanding the behavior of cache memory, or if you want to understand the behavior of cache memory, then it is important to understand important to know at least one cache simulator properly. And I think ChampSim is a easy to understand simulator, so that's why I advise you to start using ChampSim as early as possible. Okay, so now I'll move to a different topic. So I'll use whiteboard here to explain this concept. So suppose there is a matrix here. So this is easy to understand the two-dimensional matrix in a programming language, but you have to understand that in memory we call it as a byte addressable memory, right? So suppose in main memory there is not no concept of 2D, right? Everything is a one-dimensional thing. So suppose this is your memory. I'll say M1. This is the design one memory. So here these row will be stored either in one row at a time or one column at a time. So let us store one row at a time. So this will be the first row. This is row one. So what are the values here? Values will be A00, then A01, then A02, then A03. Okay, and then the second row will start from here. This is second row. Here the values will be A10, then A01, sorry, yeah, A10, then A11, then A12, A13, like this. And this is row 2, suppose, sorry, row 0, row 1, and then there will be row 2 here, and there will be row 3 here, suppose. Uh, just 1 minute. Row 2, row 1, row 2, row 3. Okay, so this is called row measure order. Row measure order means we are how we are storing this array in memory. We are storing first row 1. This is row 1. This is row 2. This is row 3. Sorry, row 0, row 1, row 2, row 3. Okay, so first we are storing row 0, then we are storing row 1, then we are storing row 2, and then we are storing row 3. So this is the sequentially we are storing in a one, because our memory is 1D, right? It's the byte addressable memory. So I think these concepts is easily, you can easily relate that if this is there is an element here, then the corresponding location in memory is very easy to calculate, right? I'm not explaining all these things. Another way to store the same array in memory is, suppose this is another option that you can use, is called column order. So in this case, the first column will be stored here. This is your C1, and the first column, the values are A00, right? And then A10, then A20, and then A30. This is the first column. Then the second column you will store here. Second column C1, third column C2, and then fourth column C3. So here we are storing one column at a time, C0, then C1, then C2, and then C3. In both way you can store. If you are storing in a file as mentioned in M1, that is called row measure order, and if you store it as shown in M2, then it is called column measure order. Now let us write a small code for integer I equal to 0, I less than, suppose, n, I plus plus, and then for forgot about a syntax. Syntax is not so important here. J plus, and then after that here I need to write Aij is Aij into 6, suppose. This is a program that I want to execute. Okay, so you have a C program, this C program, and you want to execute this program. So assume that this is your cache memory. Just 1 minute. This is my cache memory. Okay, So now let us try to find out which are the blocks that will be requested by the which are the element that will be requested by the core. First, it will request for A00, right? And then it will request for A01, then A02, then A03, then after this it will request for A10, then it will request for A11, like that. Is it clear? Because just check this line. If you check this line, then you will understand that why I'm saying this. First it will go for zero, first it will go with all ij. See the ij, so 0 1 0 2 0 3 0 0 0 0 1 0 2 0 3, and then I will be incremented. So next request will be 1 0 1 1 1 2 1 3 1 4, like this. So this is how the request will the core will request for this element. So now when and assume that here I'm saying in block size I'm not mentioning, just I'm saying in one block there are two elements will be stored. So suppose this is element 1 and it's element 2. So this is the block size. Maybe you can consider it as 16 byte of block size. I am assuming that one element is taking 8 bytes, so 16 byte block size. So first time when call will request for A00, see the cache is empty, right? So I'll go to cache memory, I'll go to main memory and fetch the block. So let us just assume that memory stored the array S for M1. So just concentrate that M1 is your main memory. So when the core will request for A00, there is a miss in cache, I'll go to memory and I'll fetch the block from the memory. So which block I'll fetch? I'll fetch this block. This is one block, right? So this block will be here now. A00 and A01 will be in the cache because these are in one block. Okay, and then A00 will be sent. Now the next core will request for A01. When core will request for A01, there will be a hit in the cache because A01 is already fetched from the lower level. That is called, this is called spatial locality, right? I already explained you. After that, the next request is for A02. Again, for A02, there will be miss in the cache, right? A02 is not here, so we'll go to memory, and then again from memory, we'll fetch this part and we'll store it here, right? And this is A02 and A03. And again for just 1 minute. Again for A03, there will not be any miss because it will be hit in the cache. So this same way it will continue. Then next block will be here. This is the next block, and then this is the next block. So A10 and then A11 will be here, right? And then A12 and A13 will be here, and this way it will continue. So this is according to M1, right? Row measure order. If we go to column measure order, then what will happen? Let us just delete everything from the cache. Assume this is your cache memory, and I want to go with column measure order. So first, program is same. The same C program we are running, but only thing is that instead of M1 memory, store the matrix in this format at in column measure order. So when it will request for A00, obviously there will be miss in cache. So I'll go to main memory and I'll fetch the block. So this is the block now. So I'll fetch the block here, A00 and A10. This is the block. After this, the next request is A01. So there will be again a miss here for A01 because the data was stored in column measure order and you have collected this data from the memory and you are expecting at this moment 01. So again there will be miss. So again you will go to memory and you will fetch one more block here. So this block will contain A01 and A11 will be stored here. A01 and A11 is here, right? So it will store it will fetch this, and in next cycle it will and next when it will request for A02 here, A02, then again you will face a miss. So you will go to main memory again and you will fetch just 1 minute, A12, and so the block will be here like A02, A12. Okay, so after the first line, when the you will start incrementing from cache will start requesting from this point 10, when now the first iteration of outer loop done, when the value of I is 1 now, then in that case the core will start requesting for A10. So when it will start requesting from A10, see, you will get a hit here. Then for A11 you will get a hit here, A12 you will get a hit here. These hits are you are getting because of spatial locality, not exactly spatial locality. Here you fetch the block previously, but blocks are still in the cache. That's why you are getting hit. Okay, so in both the cases, you will see that we are getting miss and hit both, right? So we'll get miss, but since we are fetching a larger chunk of data in the cache, and the data and the block is still in the cache, so we are getting hit after some time. But the problem will be if your cache size is less and the entire array is not possible to fit in the cache. Suppose this is your cache. This is your cache where only two blocks you can store. Only two blocks you can store. So now the problem you will face in, if you go to row order format, then first time you will A00 and then A01 will be here. This is your first block. Okay, and second block will be here. Second block will be again A02 and then A03. This is your second block. Not much problem. Yes, why I'm saying this? Because here first it will request for A00, there will be miss, I'll fetch this block, and second time when it will request for A01, there will be hit in A01. Again for A02 there will be miss, I'll go to main memory, fetch the complete block, and for next time when I'll request for A03, then there will be hit for A03 here. So far it is very good. Now when I'll request for A10, then what will happen? For when I'll request for A10, then I have to fetch a new block, right? And the new block is this block I have to fetch in the cache. Now my cache is full, so I have to remove something. So in that case, I'll remove the first block, suppose here. In this case, now the new block A10 and A11 is come. Okay, so in this way it means that only the most recent block will be in the cache, other blocks will be removed. So now that will create a problem if you go to column measure order. In row measure order you are still getting the same number of hits and misses here, but if we go to column measure order, then what will happen? This is your cache, only two blocks are allowed. Okay, now I'm going with column measure order, and I'll start requesting from the beginning. A00. When it will request for A00, there will miss in the cache, will go to memory and fetch this block. This is the block. Very good. Now next time it will request for A01, so I'll again go to memory and I'll fetch the block A01 and A11. This block will be in cache. Okay, so there are two misses again. After this I'll request for A02. When I'll request for A02, I'll again go to the memory and I have to fetch this thing, this block. So now when I'll fetch this block, I don't have any space here, so I have to remove the first one, and in place of first one I'll store A02 and A12. This is the next block, right? Now the next request is A03. So if you continue in this way, then you will find that for if the underlying memory, the array is stored as column measure order, then for this program everything will be miss here. You will not get any hit. You will not get any benefit of spatial locality. Previously what I said, the cache has infinite space, right? In that case, though we are not getting the benefit of temporal locality because the way the program is written, no element are accessing twice, right? But at least we are getting spatial locality, and because of spatial locality we are getting some hits. And that hits we are also getting in row order format, a row measure order format, right? But if we go with column measure order format, then you are getting no hits, everything is a miss. So if you write a program like this, if you when you write a program, you will simply write a program like this and you think that everything is fine, right? But if the underlying memory alignment for this 2D matrix is column measure order, then what compiler can do, compiler can change your code. A compiler can change your code to this. Instead of this line, compiler will write this line: a j I equal to a j I into 6. Compiler will write this line if it is column measure order instead of row measure. So if compiler this instead of this line, if compiler will write next line, then what will be the request will be A00. Okay, After A00, request will be for A10, and right, A, because this is J, and then request will be for A20, and then request will be for A30, like this. So in this case you will get some you will get hits in the cache. So but the example that I'm showing, the purpose here is to explain you that whenever you write a program, sometimes it is the responsibility of compiler also to understand the underlying memory alignment, and based on this sometimes the compiler can also change your code. Even if you write aij, the compiler may change it to aji. uh, and if as a programmer you also know the underlying details of a memory, then also you can also write a code like this, in this format instead of the first instruction here. Why? Because this is giving more benefit. This particular program will execute in much faster way. Or if you have written a code like this in this format, but the compiler knows that underlying memory is a row major order, then compiler will convert your code to the first one. So you can, as a software engineer, you also should know some basics. And even if you think that no, if the compiler is doing this job, then what is so important that we are discussing it here? That, and that point I think I've already explained, because you will be the one in future will design the advanced compiler. Like maybe in future you will be also assigned to a task that you should design a new compiler. In that case you should know it, right? You are a software engineer, and designing compiler is also a part of software engineering, right? So that's why, since we are here as a computer engineer, so we should be ready for any task. It's not like that we will every time we'll just write a simple C or C++ or Python program, right? It's not like this. We can do, we should be ready for this type of system level programming also. And believe me, uh, the demand of this type of programmer who know the system level programming, who know the underlying architecture, who can work on cache coherence, who can work on on compilers, the demand of this type of peoples are very high, because nowadays everyone knows how to write a machine learning code. I'm not saying that these are not less important, they are also important, but at least many people know how to write a code in Python, right? But how many people know how to write a compiler for Python? So think on this direction also. Okay, so I hope this point that that I've explained here, you understood this point. So whatever you can see in this whiteboard now, this part is not given in the book, so you have to understand it from the lectures only. I'll not share any slide because I don't think it is required. You can quickly note it down in your notebook also, because I think the concept that I've explained is straightforward. You just need to understand what is called row measure order, what is called column measure order. If these points are not clear, then you can just watch my lecture again. But I think the row measure order, column measure orders are explained in the book also. The only thing, this program is not explained in the book because they have directly started with matrix multiplication. But I thought before going matrix multiplication, let us explain you with a simple program. So now we'll understand one more example based on matrix multiplication. So if we go with for matrix multiplication, then how our suppose this is one matrix. I'll write two matrix of same size. Okay, so these are the two matrix, and I want to multiply their content. Okay, this is A, this is B, and C equal to this. I want to do this. So normally how we write this code, if we, I think it is well known to all of us, right? How we normally write. If I go here and if I write matrix multiplication, and if I just, I think if I go to Wikipedia, and then I think this formula is well known to all of us, right? The formula that I'm just showing here, A, B, and then result is C, right? C is equal to A multiplied by B. And for each element in C, that is Cij, is actually executing like this formula. So I'm not explaining it because I'm assuming that it is well known and you know it, how what is called matrix multiplication, right? So now if we want to write a program for it, then we can write for I equal I from 0 to n, See, ignore the syntax. I'm not writing the syntax properly. Then for j again from 0 to n, and then maybe there will be a variable here. Suppose cij equal to 0. This is a variable, and then for k again 0 to n, and then here I'll write cij. This is a variable plus equal to a, I think ik into b kj, right? And then here you'll write cij is equal to cij. So I think there should be a curly brace here. This is how matrix multiplication works, right? So normally if we just consider one element of C here, if you just consider one element of C, I'll not consider all the elements of C. I'll only consider, for suppose this one is C00. So how to write C00? To write C00, what we need to do? We need to do A00 into B00 plus A01 into B10, right? We need to do this, and this means A00 will multiply with this, okay, and then A01 will multiply with this, plus then A02 will multiply with B20, plus A03 will multiply with B30. This is how we generate C00 here, and then same thing will go for C1. So this and this, right? This is how I normally explain matrix multiplication. We'll go this and this in one row for A and one column for B, right? We'll go then it is C00. Then I will go for one this row again and this column of B again, and this is for C01, right? And then for same row here and for this column of B will go for C02, and for same row here and for last column of B will go for C03, and then we'll go for C10 here. For this we'll go for next row of A here, and then first column of B here again, right? So this is important to understand that here this will normally go for one column, one row of A and one column of B. Okay, so now if here you can understand that if what will be the number of misses here. So first let us understand what will be the number of excesses here. So in last time also, in the last program that I have written in the whiteboard, in the last program I missed that point, that what will be the total number of requests, or the total number of requests in that case will be n square, right? N square, because if you remember that code, I'll not that program. Now here how many number of array element request will be there from the from this program. So see, this line will be executed how many times? N cube time, right? This time line will be n cube time, and here there are two arrays A and B, right? So total number of element requests including A and B will be 2 into n cube. And plus here you can see this C element Cij, this is requesting every time once, right? So total number of requests will be n square, assuming the size of all A, B and C are n into n. So this is the total number of elements will be requested from the core here, 2 n cube plus n square. Okay, and now out of this request, how many will be hits and how many will be missed in the cache memory? That depend on the size of the cache. First, if I assume that if the cache is large enough and both A and B are fitting in the cache, then there will be very less, only the minimum number of misses will be there, right? First time if there is a miss, I'll go to memory, I'll fetch a block, and then remaining element that is stored in the block will be hit here, right, according to the spatial locality. But here and also suppose see here you can see here for each row of A we need to calculate with each column of B. So you can say that no, I'll store A in row order format, B in column order format, and this will reduce the number of hits. Maybe possible, but storing one array in row order format and another in column order format may be difficult. But even if you store it in this way, then also this is not the optimal solution. Even after that also you can reduce some misses. I'll give you an example here. Even if you store B in column measure order, assuming that we are accessing one column at a time from B, but if your cache memory is not big enough, maybe you have space to store only one column. So in that case, when you will request for this column will be in cache, fine. Now when you will request for this column, the first column will be removed from the cache. So, and if you understand the matrix multiplication, we have to read each column of B multiple times. How multiple times? I think I have explained it. I'll explain it now again for those who have not understand it yet. So what I said, that if this is your A, for each row here, I'll request this column. Then for each row, I'll request the second column, third column, fourth column. When the first row of A done, then when we'll start working with the second row of A, for second row again, I'll read column number 1 of B, then column number 2 of B. It means that the columns of B we are reading multiple times. And if only one column you can store in the cache, then when you read the second column, first column is gone. So after reading second, third, fourth column, when you again want to read column number 1 from B, then column number 1 is not there in the cache, right? So it means that even if you maintain row measure order in A and column measure order in B, then also there are some misses are still possible. Some misses are still possible. So the next question is, can you reduce the misses even more? So I'll give you one more example here, one more idea here. If you follow that procedure, then you can reduce the number of misses. So let us discuss that point now. So I think that point is better discussed in the textbook. So I'll directly go to textbook. Otherwise, I have to draw the matrix here. So I'll explain it. So see, this is the matrix multiplication code they have shown here. The way of writing syntax is a little bit different, but almost similar code they have written, and they have explained the code in chapter 3 also. That chapter we have missed, but you can go to you can click here, and then you will get the actual code, because the complete code is not written here, matrix multiplication code. And if you read the section, they have also mentioned the same thing. See, the total number of in OS case, there will be 2 to the power n cube plus n square memory access, assuming that every new request is a miss. Okay, but how efficiently we can write it, there is another efficient technique I'll discuss here. Here we can assume, instead of the only limitation that we are discussing here is that our cache is not big enough to hold all the arrays. Okay, so if the cache is not big enough to hold all the arrays, then there will be different high number of misses, right? So how to reduce that misses? So here, what we can do here, we can work as a in a block. Suppose this is the block from A, okay, and this block is from B. Okay, don't go with their block size. Just concentrate on the block size that I am designing here. Okay, so I'll go with one block of A and one block of B, and this is my block size. Okay, 3 cross 3. This is my block size. And assume that this block can be placed in the cache. Means one block from A and one block from B can be easily placed in the cache. Now what we'll do, once we load this block, suppose this block I'm saying is B1, AB1, suppose first block from A, and BB1 is first block from B. So when these two blocks will be loaded in the cache, okay, then what we will do, we'll try to use them only in such a way that we no need to load them again. Because if you remember the matrix multiplication here, I have shown, so here the array B need to be accessed multiple times, right? Each column here you need to access in multiple times. But what we are saying here, you will divide both A and B in multiple blocks, and will load one block at a time in the cache, for which we have enough space in the cache. And now we'll use these two blocks in such a way that we'll complete all the requirement of these two blocks before removing them from the cache. And once we remove them from the cache, we should not request this block again. So we have to do something like that. So for this, we need to change the code. So what we will do here, for based on these two A and B, suppose there is some one more space available in the cache where we can store at least one uh, one block of C also in the memory. So in the cache. So first we will try to calculate this point C00. I already written the code for C00, right? So C00 code, let us write it here again so it will easy for you to understand. So C00 means C00 means A00 into B00 plus A01 into B10 plus A02 into B20 plus A03 into B30, right? That you need to calculate. But we cannot calculate this part now. We because assume that in cache we have only these two blocks. So from these two blocks we can calculate the first part. At least the first part we can calculate, right? The first part 00 A00 B00 A001 B01, that we can calculate, right? So that will calculate and store it in C. So I'm writing this C as a red dot, means C00 is not complete now. C0 is not complete because it is partial, because this part is not yet done. Only the first part, this half has done now. So what we are doing here, the same matrix multiplication will be applied here for for each row here. We'll go with each column here, and then for each row we'll go for these columns again. And since this column, this is a small box, right? This is a small block here, and I'm saying the block is fit in the cache. So when within the same block of B, if I come back again to the column 0, then there will be hit in the cache, right? Because I'm saying the block is fitted in the cache. Okay, so for each row I can I'll read it. Then for next row, when I'll read again from this block B, these blocks, then all these blocks are again available in the cache. So we'll continue this small multiplication. With this small multiplication we'll fill all these values here for C. And again, you have to understand that all these values like C00 are partial values. They are not the full values, because the full array of A and B are not in the cache. Okay, so once this is done, what we will do, we'll move the block B will move from here to here, here to here. Now this will be my next block. This will be my next block in B, and in A also I'll move the block from here. Let us move from this block to next block. Now this will be my next block in A. Now again the same operation will start. Now if again same operation will start, means I'll perform for this and this. So what will happen here, I can perform this one A02, right? A02 012. Okay, so I think there was a mismatch here because the array size is high here, right? So the explanation that this formula that I have taken, I was assuming 4 cross 4, right? So in 4 cross 4 means block size should be 2 cross 2. So but so I think maybe you will confuse. So what I'll do, I'll just quickly resolve this error. Assume that block size are 2 cross 2. If block size are 2 cross 2, then I think the formula was correct, right? The previous, whatever I've explained, there was a mismatch because the formula that I've written here was according to this diagrams, and here I assume 4 cross 4, but here this diagram is not 4 cross 4, right? That's why there is a mismatch between formula and the diagram here. But I think if you go with a small 2 cross 2 block, then I think now is matching. So now after this diagram, this block, on this block is finished, we'll go to next block here for B, and here this next block here for A. Okay, so in this case now we can calculate this part, right? We can calculate this part because A02 B20 and A03 B30 is now available here. So in this way we'll complete this, and after this we'll move to next part here, and next part after this 3 move, I think the C00 will complete, means here all the values will be complete here. Once all these values will complete, then these values are done. Now we'll may start calculating for these values. So if we, so main idea here is, you can see for all the array here A, B and C, if you are loading a block in the cache, then you are completely using it And when you are removing the block from the cache, in future you will no longer require it for this matrix multiplication operation. Okay, for maybe for other program it is required, for at least for this particular program, if this is a matrix multiplication program, once you load a block in the cache, then you are using it completely, and once you remove it from the cache, you again it is not required to load it again in the cache. So this is how, if you do this, then you can reduce the number of uh, word accesses to at least 2 to the power n cube by b, where b is the block size, plus n square. So excesses, number of requests will be less here, because it will be 2 to the power n cube by b, but b the block size plus n square. So in this case, number of misses will be also reduced. So I think if you scroll, if you go up and start from the beginning of this section, see, first they have explained the basic multiplication operation, and the disadvantage of basic multiplication operation. And then if we go with blocking size, then see, from here they are calling one block at a time and then performing multiplication for one block. So I'm not explaining the code, because I think I've explained it from this diagram, so I think you will understand it. And after this diagram, they've explained that why this blocking factor is improving, reducing the number of misses. So all this thing that I've explained so far, it's maybe the duty of software developer, or it may be the duty of compiler. Sometimes even if a software developer does just written a matrix multiplication code like this, but if the compiler is smart, then compiler can convert this code to a block level design with blocking factors, right? So before that, compiler will check that if these two metrics are enough, it can be fitted in the cache or not. If it is not possible to fit, then compiler can go with the blocking factors. So it means that the smartness is not just enough, not just enough to apply in the modern softwares. Your compiler must be smart enough also, right? So if the compiler is smart enough, then it can go with blocking factors, and it will reduce the number of misses. And once the number of misses will be reduced, then your program execution will be faster. And these type of improvements is not possible to understand by a normal software developer. And that's why even if you want to be a good software developer, it is important to understand the underlying architecture behavior. So I hope these points are clear. And after this, if you scroll here, there are two more points here written: global miss rate and local miss rate. This is very easy. Global miss rate and local miss rate are in terms of memory cache hierarchy. If there are multiple level of cache, L1, L2, there are two level of cache, suppose, and this is your core, and core is requesting. Then global miss is total number of cache access, or total number of requests of this core, divided by the total miss of this L2. So suppose total miss of L2 is M, and divided by total request of by this core is R, then M by R is your global miss rate. And what is local miss rate? Local miss rate, total request reach here in L2. So suppose this is R dash. Obviously R dash is less than R. Why? Because whenever a core would request for a block, if there is a hit in L1, then we will not go for L2, right? So if there is a hit in L1, then there will be return from L1 only here. So obviously the value R will be more than R dash, because the R dash means only those requests who are missed in the L1 case, those will only come to L2. So local miss rate means M by R2. Miss rate means miss per memory access, right? Not R2 R dash. Miss per memory access. So M by R is for global memory miss rate, and M by R dash will be your local miss rate. So rest is explained here. I hope you'll understand from this section. But this is important. You should know what is called global miss rate, what is called local miss rate, when there are multi-level caches are there. And this the graph is showing the performance difference between the two matrix multiplication operation. This first one, this graph is for uh, the unoptimized matrix multiplication, and you can see the second one is for optimized matrix multiplication. And G flop means giga floating point operation per second. So more this G flop value is, the better the computer, or better the performance. So you can see the performance is improved if we go with blocked level matrix multiplication. So again, you can ask that, can we test it by yourself? Obviously, you can test it by yourself if you know ChamSim. If you know ChamSim, you can write two different versions of matrix multiplication, take a huge size of matrix, two huge size of matrix A and B, which is very common in modern machine learning based application, right? Here, even if you are working on image processing, we want to do matrix multiplication very often, right? So well, you can see why a cache memory is very important, or why knowing the underlying architecture is very important, because the very common thing required in convolution neural network is we have to go for matrix multiplication, right? So you can also do this type of operation in ChamSim and try to, and you can see that how the behavior is changing, or how the performance is changing. It will be very interesting to see. The only thing the only thing that at the beginning you need to spend some time on ChamSim. So every simulator in computer architecture, if you want to work on it, you need to spend at least 10 days on it. So how it works, how it behaves, because normally these simulation tools are not designed by designed by any industry, right? They are designed by academic people, and that's why the documentation are not very strong. And you cannot blame them, because we are also like this only. Like if you design something for assignment or your project, you will not document it properly. So documentation is less, but whatever documentation is available with this that document, you have to understand ChamSim. You can take help from my TAs, and once you know ChamSim properly, then all this experiment that is showing here, you can do it by yourself also. Okay, so this is the summary of this section. I'm not reading the summary here. So the next section is 5.5. And so what I'm doing here, I'll go here better to check from here. Then at this moment I'll skip some section, because I may come again for this section. So 5.5, 5.6, and 5.7 I'll skip, and after 5.4 I'll explain 5.8, and after explaining 5.8 I'll explain some concept of from 5.9 and 5.10, and after completing 8, 9, and 10 I'll come back to this three, these two, 5.6 and 5.7. 5.5 I think I'll skip. So the bottom line is I'm skipping three sections now, and I'm starting 5.8. But since it is already, I think 2:54, then I think I should stop here, and I let me check if you have any questions now. Do you have any questions? The race memory is linear. How can we take data in a block from non-adjacent column of rows? Yes, memory is linear. How can we take data in a block from non-adjacent columns? Or no, we are not taking from data from non-adjacent column, right? Can you explain it in more detail? What actually I'm not getting what you're saying. I'll try to explain it the way I understand. See, if you have a
Yes,
matrix,
sir.
can you I'm not getting your question actually.
Yes, sir. I try to explain. Uh,
Suppose
sir.
this is your matrix, right?
Okay, sir.
Okay, so now if I say it is stored in row measure order, then what how it is stored? Row 1, then row 2, then row 3. I'm assuming their index is static from 1, 3, and row 4. Okay, and if it is column measure order, then that's column wise will store. Now what is the question?
Sir, let's say you take the top left four blocks.
Top left 4 blocks, these blocks.
No, sir. Like in the block segment, like ऊपर के दो rows और ऊपर के इधर के दो columns. तो
ऊपर के 2 रोज, अच्छा ये इंडेक्स से बोल सकते हो, ये 0 0 हो गया, ये 0 1 0 2 0 3 हो गया, कौन कौन सा लेना है?
सर 0 0 0
हाँ,
1 और दो जो उसके below है.
अच्छा ये वाला
Yes, sir.
हाँ.
But in actual memory, they are not adjacent. Like they are not in like linear fashion, I would say. So
दे आर
हम
नॉट दे आर नॉट एडजेसेंट. अगर आप कॉलम रो ऑर्डर पे जाओगे, तो फिर ये 0 0 और 0 1 यहाँ पे है, और ये बाकी दो तो नीचे होंगे. हाँ, यहाँ पे होंगे, नीचे होंगे, यहाँ पे
yes,
होंगे.
sir. So
हाँ.
yes, sir. So like as you explained, like we can take these four uh, uh, in the blocked matrix
Acha, acha,
multiplication.
acha, acha. So you are saying about when we take our blocks, yeah. So this so when you go from blocks, then maybe when you will read this two and you will read this two, then if suppose you are reading from A, then if obviously suppose if you read this two, then I think one block में आ जाएगा. And I said the assumption I have taken here for that two entries per block. So this I think कुछ delete करते हैं. I think color का कॉम्बिनेशन प्रॉब्लम रेड कलर से लेते हैं नया मार्किंग के लिए. सो आई थिंक दिस टू एक ब्लॉक में आ जाएगा, राइट?
Yes, sir.
Yeah, and next two will come in again one block. So here also if you request for fast row, then I think स्पेशल लोकेलिटी काम कर जाएगा. बट अगर आप एरे बी के लिए बात कर रहे हो, इफ दिस इज योर metric b and b is also stored in row order, in that case this problem will not. In that case if you want to, if I go here एंड अगर मैं ये सोचूं कि मेरा जो मैट्रिक्स बी है वो रो ऑर्डर में नहीं है, वो कॉलम ऑर्डर में है, आज नहीं जाना, इधर से ही बोल सकते हैं. अगर ये ब्लॉक मुझे लेना है बी में और बी स्टोर इन रो ऑर्डर, देन वो प्रॉब्लम फिर से आएगा. लेकिन हियर व्हेन यू चूज द block size, then what we are saying that block size choose करने के time you have to choose in this way that at least uh, the block size of matrix should match with the block size of cache, means it should be multiple of the block size. Here if we say that no, block size will be 3, then every time my cache block is of 2 elements, so आपको यहाँ तक fetch करना पड़ेगा, right? But your concern is fine. Then even if you want to consider a block from matrix B and then the row order और column order का issue है, तो वो same problem तो आएगा. लेकिन वो problem यहाँ पे आएगा कि advantage यहाँ पे है कि you are loading a block, maybe when you load a block because of this column order and row order थोड़ा बहुत miss आपको इधर उधर हो सकता है in A और B, but once you load a block उसका full use कर रहे हो. Temporal locality यहाँ पे ज्यादा काम कर रहा है, क्योंकि एक कॉलम जो है बी का वो मल्टीपल टाइम एक्सेस होता है और दैट इज कॉल्ड टेम्पोरल लोकेलिटी. तो टेम्पोरल लोकेलिटी का फुल यूज हो रहा है यहाँ पे. इज इट क्लियर?
Yes, sir. But last thing, like how will you actually put the block from the memo, like put the data from the in a block from memory to the cache, because like हम adjacent लेते हैं ना blocks में adjacent data fields.
यस यस यस.
तो यहाँ पर सर जैसे रो 1 के हैं और कुछ रो 2 के हैं. If I combine a block, so like you have to jump some data in between to go to row 2 in a row
सो
fashion.
जंप तो कर सकते हैं ना. सी ओनली प्रॉब्लम इज सपोज मैं अगर A00 लिखा ना, मैंने वही बोला ना, A00 लिखा तो डिपेंड करता है कि व्हाट इज योर कैश ब्लॉक साइज. अगर आपका कैश ब्लॉक साइज 2 ब्लॉक का है, सो व्हेन यू विल रीड फॉर A00 आप एक ब्लॉक रीड नहीं कर सकते यहाँ से, यू विल रीड दिस टू. ओके, so and suppose after A00 A01 you want to skip all these thing, and if you want to read A10, then no problem. You know, according to matrix multiplication 100 से we can easily find out what is the starting address of this. We'll go to A10 and उसका जो block है उस block को हम fetch करके लाएंगे. This is easy, right? We can do it, right? We no need to go to sequential way because we know the indexing and any point. And if I'm pointing in this location, suppose ये इंडेक्स के बेसिस पे हम कैलकुलेट करके बोल सकते हैं कि इसका एड्रेस क्या होगा, because it is a 2D matrix and we know the base address also, right? And size is also fixed. So we can directly go to, suppose ये जो यहाँ पे जो सर्कल बनाया हमें उसका एड्रेस यहाँ से स्टार्ट हो रहा है, तो मैं वहां जाऊंगा और वहां से जो जो ब्लॉक आ रहा बन रहा है वो ब्लॉक को उठा लाऊंगा. Okay. Any other questions? These two rows are stored in different block in the cache. These two rows are stored in different blocks in the cache. I think I have answered this question also, but if somehow if your two elements are stored in two different blocks, then you have to move both the blocks. These two, yeah, I think it is clear now. Any other questions? So it is already, I think 3:1. So I think I should stop here. If you have any other question, you can ask me through email also. I'll try to reply. And I'll remind you again that if you have sent me any email regarding the corrections of your quiz or midsem, you have to. I'll assure that I'll do that. If I forgot, then just send me a reminder. Don't think that I'm ignoring your mail. Sometimes I forgot because I receive so many mails. Okay, so I'm stopping it here, and you may also leave now. Thank you for joining.